In this video, we're going to discuss naming simple compounds. Now, in the very early days of chemistry, as new compounds were discovered, they were given common names that were germane in the field that people knew. So these simple names were things like water or sugar or Epsom salt or, whatever for the compound that was discovered. But as chemistry started to grow as a field, it quickly became apparent that we needed some sort of systematic way to be able to name compounds as we started to discover more molecules. In the early days, this was fine just having, common names for everything because there weren't that many compounds discovered. But once we started to get a general framework of how chemistry worked and started to discover more molecules, it became apparent that there had to be some sort of systematic way to be able to just write a molecular formula and come up with a way to identify it in words. So we're going to talk about how to name a few simple compounds here and just the rules that govern how they're named. We're going to cover a few types of situations where there are systematic rules to naming compounds. A lot of them will center around something called binary compounds. So binary compounds are simply compounds that just involve two elements. Right. So basically any compound that just involves two unique elements. And I'm being very specific here, just two elements. So there can be more than two atoms in a binary compound, but it only involves two unique elements. All right. So with that definition out of the way, we're going to cover a few different scenarios of naming compounds. So the first one is going to be binary inorganic compounds. Right, so for binary inorganic compounds, so this is going to be any type of compound that involves a mixture of metals and non-metals, right? So, and there are going to be two scenarios within this type of compound. So we'll have a type 1 and a type 2. And when we start to talk about them, we'll talk about what differentiates type 1 from type 2 binary inorganic compounds. But just know up front that there will be two different types of those that we'll look at. The next thing that we'll look at will be ionic compounds with polyatomic ions, right? So ionic compounds with polyatomic ions. And in the previous video, we talked about polyatomic ions, introduced what they are. Those guys can get involved in molecules, right? So forming ionic compounds, they have a charge. So if a polyatomic ion has a positive charge, it can get with an anion to form a compound. So we'll talk about those and look at how we go about systematically naming those compounds as well. Then we'll talk about binary covalent compounds. Right, so these are compounds that have a covalent bond rather than an ionic bond, but still only involve two elements. We'll talk about how we systematically name those compounds as well. And then finally, we'll end with acids. And we won't go into too much detail about what acids really are. I'll introduce them, but it's something that we'll talk about a lot later in the course. But you should be familiar now with how we actually name acids as a part of this systematic naming system. Okay, so with that introduction, let's jump right into the first type. So the first type that we'll look at are binary ionic compounds, and this is the type 1 binary ionic compounds. And this is the three rules to name any binary ionic compound, the general rules for that. So the first rule is that the cation is always named first and the anion is named second. So you want to look at an ionic compound. You want to identify what's the anion, what's the cation, and the cation is going to be named first and then the anion will come second in the name. The second rule is that a monatomic, which means just one atom, a monatomic cation takes its name from the name of the element, right? So for example, if you have a sodium cation, you would just call that sodium. So you see Na plus, that's just going to be called sodium. And the third rule, last thing you need to know, would be a monatomic anion is named by taking the root of the element name and adding the suffix IDE, right? So if you have a chlorine anion, you would take that chlorine anion, add IDE at the end of it instead of INE, so you'll have chloride instead of chlorine. So with these rules alone, we already have everything we need to name at least one of the most famous binary inorganic compounds, right? NaCl, right? So we will call this guy sodium chloride. And you've probably already heard, of course you've heard this name before, right? But now you know systematically how we arrive at this name. We know that sodium is an ionic compound, right? So we have Na plus and Cl minus come together to form an ionic bond held together by those attractive electrostatic forces, right? And since sodium is the cation, it comes first in this name, right? So we would have sodium be first in the name. And we know that chlorine is the anion. So that means that it's going to come second in the name, and we're going to add the suffix IDE on the end of chlorine. So it's going to be sodium chloride, right? Okay, so let's look at another example, right? So let's say I were to write out the molecular formula Ki, right? So K is the atomic symbol for potassium, and I is the atomic symbol for iodine, right? They, in a very similar way to sodium chloride, come together and form an ionic bond, where potassium has a positive charge and iodine has a negative charge. So if we're going to follow this same naming convention here, if we identify first what is the cation, so potassium is going to be the cation. So the name of this compound has got to begin with potassium. We're just going to take that cation, use its elemental name, and have that be the beginning of the name of this compound. Now, we know that iodine is the anion. So we just have to use iodine and put the suffix IDE at the end. So we're going to have potassium iodide, right? Just replacing this suffix with IDE instead of INE. So we have potassium iodide as the name of this molecule, right? So for the last example, what we're going to look at is I almost said the name before I wrote it. So MgO. So let's look at the molecular formula MgO. So in this case is actually kind of interesting, and we'll talk a little bit more about this in a second. But magnesium is going to be the cation here, but magnesium actually naturally has a +2 charge. So this is a magnesium 2+ cation and an oxygen 2- anion. Now, in this case, that won't affect the name in any significant way, but we'll talk about how that actually comes into play in just a second. But you've identified at this point that magnesium is the cation and oxygen is the anion. So that means we're going to begin this name with magnesium, right? And then for oxygen, instead of its suffix, it'll have IDE as its suffix. So this will be magnesium oxide, right? Again, just replacing that suffix in the elemental name with IDE. So this guy would be magnesium oxide. Okay, so you've seen a few examples here. So I pointed out this example because I wanted to make it known that not every single monatomic ion is going to have a -1 charge or +1 charge. It's going to depend on the element. And so I've put this figure on this slide to denote the different common monatomic ions that you need to be familiar with. So if you look at this row in the periodic table, the halogens, right? So I'm looking at this row, right? All of these guys typically have a -1 charge. Fluorine, chlorine, bromine, all the way down. Same thing here with the first row of the periodic table, where you have lithium, sodium, potassium. These guys have +1 charges as well. But it's going to be dependent on the row in the periodic table as far as what the actual charge is, right? So oxygen naturally has a -2 charge. Nitrogen naturally has a -3 charge. And then when we get here to aluminum, gallium, indium, right, these guys have a +3 charge. So just know that it's correlated with each row in the periodic table, and these guys are going to have these common charges. Now, I didn't include the transition metals here, so that would be the ones that would be in the center of the periodic table here. These aren't included because they can actually have different stable ions, right? So they can have, so like for iron, for example, can be +2 or +3. That's what we're going to focus on type 2. Type 1 binary compounds are those formed with monatomic ions that have pretty much the same charge every time they form these ionic bonds. So how does this come into play? Well, let's say we had the ionic compound lithium nitride. Right? So let's say I gave you the name lithium nitride, and I wanted you to be able to tell me what is the molecular formula, right? Based off of what we just did, you might be tempted to write LIN, right? You might be tempted to write this just based off of what we've done so far. This would be incorrect. And the reason it would be incorrect is because nitrogen has a -3 charge. If you only use one lithium, then you still have an overall -2 charge. This compound has to be neutrally charged, right? So we want to think, how can we get this guy neutrally charged? Well, just use more than one lithium, right? If we know that nitrogen has a -3 charge, that means we'll need 3 lithiums in order to balance the charge. So lithium nitride would actually be Li3N, right? This would be the molecular formula for lithium nitride because you need 3 lithiums to balance the -3 charge on nitrogen. All right, so let's say I gave you the following molecule name. Let's say I gave you aluminum chloride. Right, so aluminum chloride, you know there's going to be aluminum, you know there's going to be chlorine. However, in this case, aluminum has a +3 charge and chlorine has a -1 charge. So again, if you just write AlCl as the molecular formula, you will be leaving a +2 charge. You want it to be neutral. So that means we would need 3 chlorines here instead of just 1, right? Whatever it takes to balance this charge. So that means that the molecular formula would be AlCl3, right? So 3 chlorines for that 1 aluminum atom in order to balance the charge, right? So let's do one more example just to make sure it's clear. So what about magnesium chloride? And if you've gotten the hang of it, try to pause the video and see if you can guess the molecular formula before I write it. So for magnesium chloride, right? Magnesium has a +2 charge, right? Again, chlorine has a -1 charge, so it won't just be MgCl, or else you would still have a +1 charge left over. So this would be MgCl2, right? Magnesium chloride would be MgCl2, right? So it's going to depend on, so the name is going to depend on the formula. That formula is going to be dependent on the natural charge for each one of these ions. So you're going to have to be familiar with what's the charge for each one of these guys, and in order to produce the correct molecular formula. Okay, so let's move on to type 2. So first of all, why do we need type 2? So for example, I gave the example of iron that can have a +2 or +3 charge. So what that means is that it can form multiple different compounds with the same ion. So for example, iron can form the following compound, iron with 2 chlorines, or it can form the following compound, iron with 3 chlorines. So then the question becomes, well, what do we call each one, right? Because we can't just call both of them iron chloride, right? So we have to have some way to be able to differentiate between these two types of compounds. So what you'll notice here is that for this molecule, this iron must have a +2 charge, right? We saw on the previous slide, chlorine has a -1 charge as an ion. So that means in order to balance this, this must be iron 2. And that means that this guy must be iron 3 plus, right? So the way that we name type 2 ionic compounds, so any type of compound where the cation can form more than one stable charge, we just put the charge, indicate the charge of the cation in parentheses using Roman numerals. So for this guy, its name would be iron, and then in parentheses, we'll put the Roman numeral for 2. So iron 2 chloride, right? And then for this guy, we would call this one iron 3 chloride, right? And this is really convenient because what this means is that your rules for naming binary compounds still remain more or less the same, right? You're still calling the cation by its elemental name, iron, and you're calling the anion by its name with the suffix IDE, right? The only thing that you're doing is adding this extra level of specification to account for the fact that the metal can form more than one type of charge. So let's look at a few more examples of this so that we got it. So let's say PbCl2. So Pb is the elemental symbol for lead, right? So what's going to be the charge on this guy? Well, chlorine has a -1 charge. So this guy has to be lead 2+ in order for this to be stable. That means that the name is going to be lead 2 chloride. All right. What about the following example? Let's see. Let's do HGO. So Hg is the chemical symbol for mercury. Of course, O is oxygen. If we look back at the previous slide, oxygen has a -2 charge, right? So that means that this mercury must have a +2 charge in order to balance it out. So mercury 2+. So again, accounting for the charge, we'll call this guy mercury 2 oxide, right? The same rules for binary compounds. All we're doing is just adding this extra level of specification. Okay, and the last example that I want to look at is Fe2O3. Okay, now this one's a little bit tricky, right? Because we have 3 oxygens. Each one has a -2 charge. So that means in total, the oxygens are contributing 6, a total negative charge of 6. But we have 2 irons here, right? So in order for it to balance this -6 charge, these 2 irons have to each have a +3 charge, right? So we'll have iron 3+. And that means that the name for this guy is going to be iron 3 oxide, right? Again, same names apply, same rules apply. All we're doing is just adding this extra level of specification with the charge of the cation, since it can change for these transition metal type of compounds, right? Okay, so next, let's look at compounds with ionic compounds with polyatomic ions, right? So this is just a table that I put together of some common polyatomic ions that you'll just have to know the names of. And I want to specifically point out some of these oxygen-containing polyatomic ions. So let's look at NO2 versus NO3. I meant to put this in the subscript. So this should be NO2 minus, and this guy should be NO3 minus. Right. So so for this example, right, you have 2 oxygens here and 3 oxygens here. The compound with the lower number of oxygens is usually given the suffix ITE, and the one with the greater number of oxygens is given the suffix ATE, right? Same thing here with sulfite versus sulfate, right? Sulfite has 3 oxygens. Sulfate has 4 oxygens, right? So the one with the lower number of oxygens is given the suffix ITE. The one with the larger number of oxygens is given the suffix ATE. Whereas the other polyatomic ions, you'll notice most of them still end in this IDE, right? Cyanide, hydroxide, peroxide, right? So we can still use the same naming conventions that we're used to. All we have to do is just use the names for these polyatomic ions. So an example of that would be the following compound. So let's say we got iron, NO3, 3. So I put this in parentheses with the suffix 3. That means there's 3 of these nitrate ions on the outside of this iron, right? So each of these has a -1 charge. So that means that the iron must be iron 3+. So we would just call this guy iron 3, right? And then we would just use the name of the polyatomic ion, nitrate. So it's just iron 3 nitrate. Another example. So if we have the chemical formula MnOH2, right? So that means we have 2 hydroxide ions. Looking at the table, it has a -1 charge. So that means that this manganese must be 2+. So this is going to be manganese 2. And then we just use the name of the polyatomic ion. So we just use hydroxide. So manganese hydroxide. Right, so this is pretty simple, same type of rules. You just have to know the names of these polyatomic ions in order to get the names of these compounds correct. Okay, so for the next one, we're going to be looking at binary covalent compounds. So the rules for naming binary covalent compounds, these are compounds that don't involve metals. All of the bonds are covalent bonds. So in this one, the first element in the formula is named first. Use the full element name. Second element is named as if it were an anion. So that means we're going to use the same type of IDE suffix for the second element in the covalent compound. Prefixes are used to denote the number of atoms present. So your standard geometric prefixes, mono, di, tri, tetra, hexa, petra, all of these geometric prefixes are used to denote the number of atoms that are present. And the fourth little warning is that the prefix mono is never used for naming the first element. So for example, carbon CO is called carbon monoxide, not monocarbon monoxide, right? So that's the first example of applying these rules. Carbon monoxide is CO, right? What about CO2, right? You probably already know this as carbon dioxide. That dioxide comes from the fact that we have 2 oxygens present, and so we use the geometric prefix di. So carbon dioxide, right? Now, what about N2O3? Let's say we had that, right? Now, since we have 2 nitrogens, we have to use a geometric prefix for the first element. You only don't use the geometric prefix when it's only 1. So this compound would be dinitrogen, right? Since we have 2 nitrogen atoms, and trioxide for the 3 nitrogen atoms, right? So dinitrogen trioxide for N2O3. And what about NO, right? So for NO, since it's only 1 nitrogen, we just call that guy nitrogen. We only have 1 oxygen, so this guy would be nitrogen monoxide, right? Just like carbon monoxide. Okay, so that's how you name binary covalent compounds. Pretty simple. Certain binary covalent compounds have common names that we just use instead of their systematic names. So for example, water, right? Water is just called water. It's not called dihydrogen monoxide, even though that would be the systematic name for it. We mostly refer to H2O as water rather than dihydrogen monoxide. Okay, so binary covalent compounds. The next one that we're going to look at is acids, the last one. So for acids, acids are a special kind of compound and they have their own special naming system. So what I want you to know for acids at this point, which we'll talk about them in much more detail later, but acids are basically compounds that have more than one hydrogen atom attached to an anion. So they have one or more hydrogen atoms attached to an anion, right? So you'll have an anion and there'll be a hydrogen atom attached. Now, there are going to be two different types that we're going to look at. So the first one are acids that do not contain oxygen, right? So if an acid doesn't contain oxygen, then there are basically three rules that you want to follow, right? So you want to use the prefix hydro. So use the prefix hydro to begin the acid name. The second rule you're going to follow is the anion suffix will be changed, right? So the anion suffix changes from IDE to IC, right? So instead of chloride, it would be chloric, right? So changing that suffix in the anion. And then you just place acid at the end of the name. So acid is at the end of the name. So a few examples of this, right? HF would be hydrofluoric acid, right? So since it's a acid that doesn't contain oxygen, so we begin the name with hydro. Instead of fluoride, it's fluoric and then acid, right? Now that's an example for a monatomic anion. What about a polyatomic ion? What if we have HCN? Right? CN is a polyatomic ion. So let's go back to our list of polyatomic ions. CN is called cyanide, right? So for cyanide, right, this would just be hydrocyanic acid, right? Instead of cyanide, we use cyanic. So hydrocyanic acid, right? So that's what you do when you don't have an oxygen. Now, when you do have an oxygen, right? So if you have an acid that contains oxygen, it's going to depend, right? So it depends on whether the oxygen ends in ATE, the anion ends in ATE or ITE, right? So again, remember we had these rules, right? So like for NO2 and NO3, you have nitrite and nitrate, sulfite, sulfate, chlorite, chlorate, right? So we're going to have different situations here. So the only thing, you follow the same rules, except you don't use the prefix hydro. And if you have the suffix ATE, that is changed to IC, right? In a very similar way as this, right? If you have the suffix ITE, that is going to be changed to OUS, right? So I'll use nitrate and nitrite as examples. So HNO3, right? If we look back at our chart, right? NO3 is nitrate, right? So going back with our rules, that means the ATE becomes IC. So this would be nitric acid. And for HNO2, right, this is the NO2 anion is nitrite. So that would turn to OUS. So this would be nitrous acid. Nitrous acid, right? So if you have an acid that contains a polyatomic anion with oxygen, you're going to have to follow these rules, versus if you have any acid that does not contain oxygen, you use these rules. Okay, so I know that was a lot, but I wanted to just make one video where we go over these naming rules. So make sure you guys practice these on your own. These rules are just something that you have to know. Sometimes I may give you the name of a compound without giving you the formula, and you might have to know that formula for a problem. So just make sure that you know these naming conventions, so you'll be able to build the molecular formula based off the name, or be able to name the compound based on the formula.